Worksheet 3, Energy Systems Quantitative. We're just practicing using the basic energy formulas here. I'll put them at the top of the page, or maybe the side, or maybe I should just get an equation sheet so you can see where they are coming from. Alright, the magic of video. So the equations we're looking at here are mostly going to be just these three. Kinetic energy, gravitational potential, and spring potential. So if something's moving, it has kinetic energy. If something is changing height, it will be changing gravitational energy. If there's a spring and it's compressed or expanded, we'll have spring potential energy. The energy will transfer between these three forms depending on what's going on. The other energy we have to concern ourselves with is internal energy. However, there's no equation here for internal energy. Typically, the internal energy is just whatever energy ends up missing. All right, so let's go back to this worksheet, and we'll have this at the ready in case we need it. 25 kilogram block starts from rest on a 6 meter tall hill, frictionless ramp, and then slides to the bottom. Determine the gravitational potential energy of the object at the top of the ramp. So we're just looking for PEG here. That's it. We're not doing anything else with this. We're just practicing calculating for the total energy, the initial gravitational energy. So equals mgh. The mass of the object is 0.5 kilograms. G is, we'll use 10 newtons per kilogram for G. And the height is 0.6 meters. All right. So 10 times 0.6 is 6. Half of 6 is 3. 0.0, and the units are joules. Ends up being Newton times meter. The kilograms cancel. We have newtons times meter. That ends up just being joules. All right, so that's the PEG at the top. Now, we'll see later on that if that's the PEG at the top, then that's also the kinetic energy at the bottom, as long as there's no internal energy buildup. The next one, a 2 kilogram block is slid along a high friction surface with an initial speed of 12 meters per second. It comes to rest after sliding a certain distance. So friction does work on the block, taking energy out of it. We don't know what the distance is. It says determine the initial kinetic energy of the block. So kinetic energy, initial. We know the mass, we know the initial velocity, so we can just use the kinetic energy formula. 1/2 mv squared. So 1/2 of 2 kilograms times 12 meters per second. And again, I'm getting this from right here. Kinetic energy equals 1/2 mv squared. Okay, so 1/2 of 2 is 1. 12 squared is 144. So it's 144. And the units are a little bit hard to see, but I know it's energy, so it's joules. A little bit hard to figure out. It's kilograms times meters squared per second squared, which is a newton times a meter, which is a joule. All right, this one here, a little bit different. 150 kilogram roller coaster cart is moving at a speed of 3 meters per second, coming over the top of a 30 meter high hill. All right, so 30 meters, it's height here. 30 meters above its lowest point, so it's going to lose that much gravitational energy and gain that much kinetic energy. Slides down to the bottom of the track where it's moving fast. About 10% of the cart's energy is lost due to friction. It's lost in that it can't be kinetic, but it's not lost because it is getting converted into another form of energy. It's just that it's not a usable energy once it becomes heat energy. So determine the gravitational potential energy and kinetic energy at the top of the hill. Also determine the total energy of the cart at the bottom of the hill. Well, whatever the total energy is up here, that's also going to be the total energy down here. So if we figure out the gravitational and the kinetic up here, add those together, that'll be what the total energy at the bottom must be equal to. So first of all, let's get the two energies, PG at the top and KE at the top. So mgh 1/2 mv squared. So it's 150 kilograms times 10 newtons per kilogram times the height of 30 meters. That's going to equal, so 150 times 10 times 30. That's 45,000 joules. 1/2 of 150 kilograms times V, 3 meters per second squared. So that is 0.5 times 150 times 3 squared, 675. So the total energy equals 45,000 plus 675. So it's 45,675 joules, the total energy. So total energy is conserved. So that's the total energy at the top and the total energy at the bottom. Okay, we'll call the E total top. So it's got to be the same at the bottom. Now, if 10% of that was lost, goes into internal, that would mean 10% of this would be internal. All right, so 10% E internal, which would leave us 90% kinetic at the bottom. So it'd be divided between the two. All right, move on to the back of this worksheet real quick. Oops. All right, 100 kilogram frictionless car is launched up a 5-meter high hill. Compressed spring at 2 meters. Compressed 2 meters. Spring constant 4,000 newtons per meter. Determine the spring potential energy stored at the bottom and the gravitational potential energy at the top. How much energy is left over for kinetic? So PES at the bottom, or initial, whatever you want to say, is 1/2 kx squared. So that's 1/2 of 4,000 newtons per meter times 2 meters squared. So it's 0.5 times 4,000 times 2 squared. 8,000 joules, and it's stored in the spring. All right. And then PEG at the top, however you want to say it, is MGH. It's going to be 100 kilograms times 10 newtons per kilogram times the height of 5 meters. That's going to be 5,000 joules. So, look, this is the energy you start off with here, right? 8,000 joules. Right now, we only have 5,000 joules accounted for at the top. So that means KE at the top is the missing 3,000. There's no internal energy. It says it's frictionless. So initially down here, it's all PES. Up here, it's PEG and KE. So 8,000 joules down here. Up here it's split. So it's 5,000 and 3,000 right there. This next one is a little confusing to students. I guess probably need a couple more drawings here, right? So showing the spring launching off the ground with some V, then it gets up to the top of its motion. The V is 0. And it's at some height h. All right, so down here it's all spring potential. When it launches off the ground, it's all kinetic. When it gets to the top of its flight, it's all PEG. So what's interesting here is these all have to be equal, right? The spring potential energy stored initially is what the initial kinetic energy is equal to when it leaves the ground, which is equal to the gravitational energy it has when it gets to the peak. So depending how much energy is stored initially, that dictates how fast it leaves the ground and then how high it goes. All right, so if we figure out the spring potential energy stored initially, 1/2 kx squared, that's going to tell us everything else. All right, so 0.5 times 1,000 times 0.03, 0.45 joules. So that means all of these are 0.5. KE, all right, KE max, PG max, all have to be 0.45 joules of energy. This one here, 5 kilogram block, starts up there, starts all gravitational energy. All right, and then at the bottom it's all kinetic. All right, so the PEG at the top has to equal the kinetic energy at the bottom plus the internal energy that's built up. This is called the conservation of energy equation, right? I made one here. I could have made one up here, right? I could have said PES at the bottom equals the PEG at the top plus the KE at the top. That is also a conservation of energy equation. So PEG at the top is mgh. K at the bottom is 1/2 mv squared. E internal we don't have a formula for. We just leave it E internal. So if I plug in the numbers here, I get 0.5 kilograms times 10 newtons per kilogram times the height of 2.0 meters. That one's not right. It's 2.0. Need to fix that. Equals 1/2 of 0.5 kilograms times 5 meters per second squared plus E internal. So if I figure these two energies out, mgh and kinetic energy, so 0.5 times 10 times 2, 10 joules equals 0.5 times 0.5 times 5 squared is 6.25 plus E internal, right? Well, E internal's got to be, you know, if you start off 10 joules total and you have that much kinetic at the bottom, then internal is whatever's missing. So internal energy has to be 10 joules minus 6.25 joules, or 3.75 joules built up. So quite a bit of the energy went into thermal energy. All right, that's that worksheet. Pretty straightforward, not too bad. I'll get these all scanned and posted, and we're moving on.